Okay, so let's get started on the reviewing some of the homework questions then. Okay, question two. Question two was about calculating the torque on an electromagnetic motor. Homeworks, there's some, I think several folks probably haven't had a chance to send it around this way. Okay. So this problem involves calculating the torque on an electromagnetic motor. No, Jeremy, did you have a specific question on this?
Yeah.
Okay.
Is it force? Okay. Is it force 1 and force 3 that you're doing, or force 1 and force 2?
That's that. I didn't know that's force 1 and 3.
Yeah, because force 1 and 2. Well,
you put 1 and 2. It's 1 and 3.
It should be 1 and 3. Correct.
Yeah,
correct.
That's
yeah.
what I was looking at.
Yep.
Or it should be 3 and 1, because I think that.
Yep, 3 and 1 is correct.
Oh, it's 3 and 1.
3 and 1.
Okay.
3 is in the negative z-hat direction, and the other one is the positive z-hat direction.
One parallel to the axis of rotation don't contribute.
Yeah.
Correct. So let's make sure everyone's on the same page here. All right. All right, so this is just continuing on the example that we did in class of a loop that's in a magnetic field. Okay, this is the basis of a motor. Okay, if you have a magnetic field and then you have a loop of wire with current running through it, that loop will tend to rotate in the magnetic field. The reason why that's happening is because of what we talked about in class. Let me just go back to the schematic here.
Is that normal vector we see there perpendicular to all 3 planes?
I'm sorry?
Is that normal vector in this drawing perpendicular to all 3 planes?
The normal vector is perpendicular to the loop.
Okay. Right.
So, why isn't this showing my...
Or the plane that the loop's in.
Yeah, it's perpendicular to the plane of the loop. Okay, everyone can see this now. Okay, so this vector is perpendicular to the plane of the loop. All right, now the key point of this is actually shown on the previous slide. If you have a loop in a magnetic field, okay, I want everyone to try this right now. If you haven't done this problem already, just to do this. Right-hand rule. Let's say we're on segment 3. Okay, so segment 3, your first finger points in the direction of current. Your middle finger points in the direction of the magnetic field. Okay, so it'll be like this. First finger up, middle finger in the right-hand direction. Your thumb should point into the page, or into the screen. All right. So now, I want everyone to try the opposite one. Now, try segment 1. In the case of segment 1, current is pointing down. Magnetic field is pointing to the right, so your middle finger is pointing to the right. And notice that your thumb is now pointed out of the page, out of the screen. Okay? So what's happening is on this side of the loop, there's a force that's pushing into the screen. And on this opposite side of the loop, on side 1, there's a force that's coming out of the page. So one is going in, one is going out. And that's basically, imagine that's what applies the torque. That's what causes that loop to rotate. Opposite forces on opposite sides. Now, we talked about this as well. Segment 2 and segment 4. Why do those segments have no force or no torque? I should say.
They're parallel to the magnetic field.
They're parallel to the magnetic field. Like segment 4 is in the same direction as the magnetic field, so 0 degrees between the two angles, and this is 180 degrees. Okay, so when you do those cross products, sine of 0 is 0, sine of 180 is 0. So if the current is parallel to the field, then you basically get no force resulting. Okay, so the same thing happens. Something slightly different happens here. Okay, starting with 2 and 4. Okay, 2 and 4 actually don't contribute torque, but let's look at what happens. Okay, so force segment 2. Segment 2 is if in the previous example, segment 2 was basically 180 degrees, so it was parallel with B, just in the opposite direction. But here you can see that it's not 0 or 180 degrees. There's some angle there. Okay, as long as there is some angle there, there will be some force that's generated. Okay, but if you do the right hand rule, so you figure out force 2. So your first finger points in the direction of the force. Your middle finger would point in the direction of the magnetic field. So it'd be kind of like this. I'm showing you here. Okay. The force is going to be, your thumb is going to point in the direction of force, and that's going to give you a force in the y-axis. Okay. So it's pulling this way. F4, the fourth segment, is also generates a force, but it's pulling in the opposite direction. Okay, so segments 2 and 4, they don't generate torque. Okay, they're generating opposite forces. Okay, so those opposite forces balance each other out.
So how's the current going?
So the current is going in this direction in segment 2 and in this direction in segment 4. They're going in opposite directions. So they generate forces in opposite directions.
Okay, isn't the magnetic field should be into the page or
the magnetic field in this case is along the x-hat direction. So the magnetic field being applied is perpendicular to the loop. Perpendicular to the loop.
So,
all right. The difference between this and this, okay, is that in this case, this is just a limited case of this general one, okay? When this angle theta is equal to 90 degrees, then you have this situation right here, okay? But this is the more general case where this loop can actually turn and that angle theta can change. Ali.
okay, so first is the I. So it's going upward, and then F, right? And then
the I, so I is going counterclockwise through the loop.
right. So F, let's say if it's on position 2.
Uh-huh.
And then so I, F, and then.
Are you talking about segment 2?
Yes.
Okay, so first finger points in the direction of the force. Looks like this. Your thumb is pointing in the direction of the magnetic field.
The magnetic field or the current?
Magnetic field. Middle finger points in the direction of the magnetic field. First finger points in the direction of current.
So the current is the blue one, right?
Correct.
So the thumb and the thumb is the current.
No. First finger is the current. First finger is the current.
That's why I got confused, because the other one, when they were doing the wires, the finger is the current, then the hand curves.
The one this way.
Yeah. So let's keep our let's remind ourselves the different right hand rules. Okay. There's one right hand rule which was the Lorentz force, and that's the same one that we're doing here. For the Lorentz force, first finger points in the direction of the current.
The thumb in the direction of
Middle
force.
finger points in the direction of the magnetic field, and the thumb indicates the force. The other right-hand rule we talked about is this one, the thumbs up with the fingers curled. Okay. In this case, the thumb is pointing in the direction of the current, and the fingers curl around and indicate what the magnetic field lines are.
I think that makes more sense. Yeah.
Okay.
That's for
So
the wire.
two types of right-hand rules.
The way we're doing it. 2 fingers and the thumb. More
Okay. So the key point here is that segment 2 and segment 4, there are forces on there, but those forces are in opposite directions, and they don't generate any torque. They're just tugging on opposite sides of that loop. Force 1 and force 3, however, do generate torque, because force 1 is in the positive z direction and force 3 is in the negative z direction. And you can imagine that this force would cause the loop to turn. The difference between this one and this one, as I said before, is that in this more general case, theta can change. All right. So what happens when theta becomes what happens when theta becomes it becomes 0 degrees? So what happens when this loop is basically
Steady state, no change. Would that be-
in the torque actually becomes the torque becomes 0 in that case.
When what becomes 0? When theta?
When theta becomes 0, the torque actually becomes 0.
They would say that it would be the specific one. Oh, no, no.
Let's look more closely at y, okay? So force 1, okay, one of the key things to keep in mind about force 1 is that force 1 is always in the z-hat direction. Okay, why is that? Right-hand rule. Imagine your first finger is pointing in the direction of current. Okay, so it's pointing down. The segment 1 is pointing down. Your middle finger is pointing. Your middle finger is pointing towards the magnetic field. So it hands like this. So the force is in the it's in the z-hat direction. Does that make sense? Okay, so and the interesting thing is this happens regardless of the angle of theta. Okay, the direction of the force doesn't change, just the magnitude of the force does. So this force is always in the positive z direction, this force is in the negative z direction. Now, think about this. When this thing has turned, when the angle theta, when this angle theta is equal to 0, in other words, when this is on top and this is on bottom, so this one becomes aligned with the z-axis. When that happens, then the force is going to be, the force is just going to tug on the loop. It's not going to generate a torque on the loop. Does this make sense?
No.
Okay. Maybe it would help if we draw it out. Okay.
Well, if theta goes to 0, that plane becomes vertical.
So
The axis.
this is the direction of the magnetic field. This is z. And I'm going to draw the loop. Okay, the loop, it'd be initially like this. So I'm drawing the side view. Say the loop looks something like this. Okay, and if I were to try to draw it in 3 dimensions, it would look like this. Okay, the magnetic field is pointing in the x direction. Okay, now the current is pointing down on this side and up on this side. So this is this was segment 1. This is segment 1, and this is segment 3. All right. So right-hand rule. Okay. Segment 1. Your first finger is pointing in the negative z-hat direction. Magnetic field is your middle finger is pointing in the x-hat direction. This is the x direction. All right, so the resulting force is, oh man, I have the segments mixed up. Segment 1 is here. Sorry, guys. This segment 1. Yeah. Yeah, because this is segment 1 is the one that's when this angle becomes 0 degrees, this loop is good. Okay, everyone take a look at this. Does everyone agree, like if this angle becomes 0, okay, if this angle becomes 0, that means the loop has turned completely 90 degrees.
So F1's on top.
F1 is on top, exactly.
That's confusing. Because it looks like the 0 angle starts at the x-axis.
The 0 angle does start at the x-axis. When that angle is 0, this thing is actually turned 90 degrees. When this thing's flat, when this is flat horizontal, that theta angle is 90 degrees.
Okay.
Okay, when theta is 90 degrees, that's actually when the torque is maximum.
Okay.
And when that theta is 0 degrees, that's when the force reaches a minimum. So I'm going to show you the case when theta is equal to 0 degrees. Okay? So this is segment 1. This is segment 3. Okay? So the if you imagine the this is in the y-hat direction. This will give you some sense. The current is going in the y-hat direction. Okay, so first finger in the y-hat direction, middle finger in the x-hat direction. That means the resulting force is in the z direction. Okay, so this is the Lorentz force here, and the Lorentz force on the other side looks something like this. All right. Now,
wouldn't that be zero since the current in the y in the F1 would be parallel to B or B?
say that again.
So if you're at F1, right? It's on top. So the current is going this way now, right?
No, the current's coming. The current's going coming out of the page.
Okay, never mind. Yeah.
Yeah, the current's coming out of the page here. So it's in the y-hat direction. Magnetic field's in the x-hat direction, and the force is in the z direction. Does that make sense?
I was trying to figure out the current. You said is going this way, right?
Yeah. So imagine the current coming out of the screen.
Yeah.
Okay, the current's coming out of the screen, so that your first finger is coming out of the screen. Magnetic field is pointing this way,
So
from left to right, and thumb is the direction of the force. So thumb is pointed up.
Okay.
Does that make sense?
That makes
Yeah,
sense.
just like your hand is right now.
It makes sense, but what I usually do is this way and that way, or positive z at positive negative z this way. So I just do it. That's not being confusing.
Positive and negative z.
Yeah, I usually do this way, it'd be x, right? And then if it goes up and down, be y, and then z in and out of the page.
Oh, but this is just drawn in a slightly different way.
That's what that was my fault though.
Okay, but it makes sense now, right? So in this case, like when it's in this type of position, the force is you're gonna end up getting a positive a force in the positive z direction on top and the negative z direction on bottom. So the two forces are going to just tug on the two ends of the loop, and the same thing will happen with the segments 2 and 4. They're also going to generate forces in opposite directions, and there's going to be zero torque on the loop. Okay, when theta is equal to 90 degrees, the situation becomes like this. The situation will actually become like the example that we just saw earlier. All right, where the magnetic field is in plane with the loop. When the magnetic field is in plane with the loop, you'll actually generate maximum torque. So we did derive this in class, but the end result is this thing here, IAB times sine of theta. This is ultimately what I wanted you to use in this problem.
A question.
Yeah.
For this type of problem, would that be consistent? Would that equation ever change?
No, for this type of problem, it won't. Yeah.
And our normal
Okay,
vector is
so-
based on which surface?
The normal vector is perpendicular to the loop.
Okay.
So when I say it's perpendicular to the loop, if you imagine the loop as a surface,
Yeah.
that vector is perpendicular to it. Okay, so that was question 2, and if you look over the solutions, it's really just this is the formula. You're given the 2 parts of the torque, and you can figure out the T1, T2, T3, T4. Notice that T2 and T4 are always 0. They never generate any torque. T1 and T3 also don't generate torque when the angle is 0 or 180 degrees. And they do generate torque at these intermediate angles. Okay.
I just have a quick question about why it's negative at the angle 135.
Yes, because when it's at 135, that means let's see. If you were to take this. If you were to take this loop and then actually turn it more than 90 degrees, okay, if you were to turn it more than 90 degrees, then, oh, wait a minute, well, 90, that's 90 degrees, 135 degrees. If it's 135 degrees, it should actually be.
Does it have to do with the relation to the current and the magnetic field as it passes?
No, let's think about this for a second.
Because like the cosine of our angle, even though we're dealing with the
90
cosine part.
90 degrees, so if it is more than 180 degrees would put it there. Anything more than 180 degrees. Okay, Justine made a good point. So Justine's point was, why is it negative, right? So if it's more than 180 degrees, then the torques will actually become negative. Okay, but at 135 degrees, the force should still be positive. The torque should still be positive. Okay. Yeah, and I want to explain why real quick. Okay, now imagine that this is the figure. Okay, this is the angle. Theta is the angle between the plane of the loop and the x-axis. Now, when theta is equal to 90 degrees, that means that the magnetic field is perpendicular, or in plane of the loop, just like you see here. Okay, so this is when theta is equal to 90 degrees. If you were to turn this thing another 90 degrees, okay, and then beyond another 90 degrees beyond that, what's going to happen is that this segment of the wire, segment 3, is now going to be on the opposite side, right? If you turn it enough, segment 3 is going to be on the opposite side. Okay, and remember, in segment 3, the current is going from bottom to top. So the force on segment 3 is always going to be pointed in the negative z direction. All right, so I want everyone to just imagine if segment 3 was on this side. Now you're pushing into the page. You're pushing into the page on this side, and you're pulling out of the page on the right side. So the torque will end up being in the opposite direction. Does that make sense, or did I lose?
There's a relation between the current and the magnetic field as it
Right.
passes that.
Right. Yeah, so David brought up a good point. It's the same, if you reversed the direction of the current, you'd get the same effect, right?
Right. Rather than a negative value, it's giving us a direction in this sense. Because it's a vector, right?
Yes, since the current is defined in a certain direction, Since the current is going up on the right side, that results in a Lorentz force pointing into the page. And the Lorentz force is pointing out of the page on this side. But if you were to turn this loop more than 180 degrees, then you're going to end up with a situation where you're going to have an upward current on the left side and a downward current on the right side. So the torques will be in the opposite direction. Does that make sense? Have I lost people there?
So then the 135 row should actually be positive?
The 135 row should be positive, yes.
Okay.
If you go beyond 180 degrees, then those values will...
Because sine is still positive.
Sine is still positive, right. Yeah, so I will fix that. Apologies for the mistake there. If you just use the sine formula, for those of you who are feeling anxious about this, if you just use the sine formula, you should still get the correct magnitude of force. Okay, so trust your math and everything will be fine.
And question, plugging in like your answers like square root of 2 or 4, just plugging in sine, right?
I'm sorry?
So like for degree 135
Mm-hmm.
under T1, I see square root of 2 over 4. That came from sine of 135, right?
Yeah, the sine of 135 is square root of 2 over 2.
Okay.
But there's another 1/2 factor here. So that's where you multiply root 2 over 2 by 1/2, you get root 2 over 4.
Okay. And that's the case for everyone multiplied by this 1/2? Just about?
Yes.
Okay.
Yes. So the beginning of the problem talks about that part. Okay. If anyone does anyone remember where that a over 2 comes from?
Is that the distance?
It's the distance from where to where?
Half of the
Minus
square.
A.
Half the diameter. Yeah. Half the width of the loop, because that's the moment arm. The moment arm extends from the middle of the loop, the axis of rotation, to the edge of the loop. Okay. Well, we spent more time than I was thinking, but that's okay. All right. Other questions on the homework? Yes.
Yeah, 8E.
8E. Okay. This is the Hall effect problem, isn't it?
Yeah.
Okay. The Hall effect I would actually like to go over. That's one of the topics I want to go over today.
Okay. Well, I'm thinking that the force vector should be in the negative x hat direction instead of the z hat. I was just wondering, there's a diagram below that you...
This one. The electron is deflected in the negative z direction. Total electromagnetic force is the sum of the electric and Lorentz force. Yes, the negative z hat direction. It results in a negative charge buildup and a Hall voltage. So the electron is deflected upwards. So what was your question? You're saying it should be in the x direction?
I was thinking so, because the part E, you're crossing the electron velocity with the magnetic field. One's in Y, one's in Z.
So the electron is going this way. Magnetic field is pointing this way. It's the Lorentz force should actually point in the positive. No, the magnetic field is in the z direction, so the electron should be deflected in the positive x direction. Wait, let me just double check this. Electrical force to the okay, the voltage is, the electric field is in the y direction. So this is a good, we can all try this together, okay? So where's the voltage applied? So in this problem, what you're doing is you're generating a current in a semiconductor material. We'll talk about Hall effect sensors. Actually, maybe we should talk about it now and then. Why don't we just talk about the Hall effect sensors now and then we'll come to this. I think that'll be a good segue. All right, so maybe we won't end up talking about inductance today. Let's just talk about the Hall effect sensors. All right. So the reason I wanted to include Hall effect sensors for this class is because it's one of those things where it's used in a lot of sensors today. It's used in disk drives. It's used in automotive clutches. It's also used in like digital compasses, the electronic compasses. And the reason I want to talk about it is because it's directly related to the Lorentz force. Okay, it actually is very much a Lorentz force type of problem. So what we're going to do here, we're just going to do a quick example, just so you see how Hall effect sensors work. Hall effect sensors, by the way, they detect magnetic field. Okay, so for those of you who've used a compass before, you're trying to detect magnetic field, which way is North Pole, and so on. Hall effect sensors can detect magnetic fields electronically, and it can be miniaturized. You can make these things super tiny. All right. So this is the bar of semiconductor material. I hope everyone can see that. This is the bar of semiconductor material. Can everyone see the arrow up there? Yes? No? Yeah. Okay. And let's say this semiconductor material, let's just say that there's it's an N-type material, so it's mostly electrons. Okay. Or just think about this as a conductive material. Forget about semiconductor. Just think about this as a conductive material, and there are electrons. Okay, electrons are the charge carrier. So if you apply a voltage across the material, notice where the voltage is applied. It's applied in the horizontal direction. Okay, so the voltage is applied such that this is the positive side. The right side is positive. The left side is negative. All right, so the electric field is pointing from left to right. Do you see this red arrow here? That's the direction of the electric field. I'm sorry, no. The electric field's in the opposite direction. This is the force on the electron. Okay, electrons, remember, electrons move opposite the electric field, correct? So the electric field is pointed from positive to negative, so it's pointed from right to left, but the force on the electron is in the opposite direction, left to right. All right, so this is nothing new. If you put a voltage over a conductor, you're going to get current flow. That's what the electrostatics module was all about, right? Now, all we're doing is we're just adding a little bit of extra knowledge to this. We're adding the Lorentz force. All right, so by applying this voltage across here, you generated a current. You generated a moving charge. Now, suppose you also have a magnetic field B here. All right, so does anyone remember how to apply the right-hand rule with electrons?
Yes, no.
Just kind of negative with that one.
Oh, yes, negative, so it's opposite direction.
It's opposite, right?
Yeah.
Okay, so this is how I like to do it. Just apply the right-hand rule as you normally do, but just negate the direction of the Lorentz force. Okay, so everybody point in the direction that the electron is moving. First finger points. You're going to be pointing from left to right. Electrons moving from left to right. Okay, middle finger points in the direction of the magnetic field. Same as before. So it's pointing the upwards direction. So what direction is the Lorentz force? Well, your thumb is pointing in. Your thumb is pointing out of the screen, and since it's an electron, you have to negate that. So the Lorentz force will be
That inside.
into the screen.
Oh, is that like going to be a clear thing? Whenever you ask a question, will you tell us if it's electron?
Oh yeah,
Okay.
yeah. I'll tell you if it's electron or proton. So that's what. So in that case, the electron will get deflected in. The electron will get deflected upwards, and you'll generate a negative charges up on the top, and you'll generate positive charges on the bottom. Now you can measure that. Okay, let's. Well, this is showing a derivation of it. Okay, now let's try a slightly different geometry, or slightly different. Let's assume that the current is going this way. Okay, let's try this problem again, assuming that the current is going out of the page. All right, so in this case, your first finger is going to be pointed out of the page, right? So electron is moving out of the page, first finger. Magnetic field is pointing upwards, so your middle finger is pointing up. So your thumb is pointing to the right, correct?
Mm-hmm.
Yeah. So okay. There's when we talk about current, okay, we were talking about the movements of electrons just now. But if we're talking about whenever we define a current I, how do we is current defined as positive or negative movement of positive or negative charge?
Positive.
Movement of positive charge, right? So when we have current here, okay, the current is going in this direction. It's coming out of the page, so that means the electrons are moving in the opposite direction. They're going into the page. All right, so let's, if the electrons are moving into the page, your first finger is pointing into the page, middle finger is pointing up. So your thumb is going to be pointed from left to right. And that's how you get this type of voltage that's formed. Okay, this is the magnetic force, the Fm. Again, electrons are moving moving into the page. First finger, magnetic field is going up. So your thumb is pointing in from left to right. The electrons move opposite the thumb, so the electrons move from right to left. So it's in the direction of Fm, so right to left here. So the way the Hall effect sensors work is that they build up a potential. There's two things that you'll do if you want to get a Hall effect sensor to work. The first thing you're going to do is you're going to apply a current in one direction, and then you're going to apply a voltmeter on the other direction. So you apply a current here. All right, and then when the electrons deflect over to this side, you end up generating a buildup of electrons on one side. What happens if you build up electrons on one side? Positive charges would build up on the other side, right? But you build up a potential, right? If you have a separation of charges, you build up an electric potential. So the simple way a Hall effect sensor works is you apply a voltage in one direction, or you apply a current in one direction, and then you measure the voltage in the other direction, in the orthogonal direction. All right, and you generate a Hall voltage, and that Hall voltage is equal to I times B divided by NQD. N is the electron concentration. Q is 1.6 times 10 to the negative 19. And D is the depth of the material. Okay, there is a derivation of the Hall effect on this slide. I just want you to take a brief look at it. Maybe jot down the formulas here. Okay, I'm not going to ask you to derive all the parts of the Hall effect because just in the interest of time. But I just want you to understand how it works. Now. Does everyone sort of have an idea of how the sensor works then? Yeah, Isaac.
Why is that I cross B? I mean, because if the magnetic field's not perfectly parallel, shouldn't that reduce the effect?
Yeah, great question. If the magnetic field is not perpendicular to it, then you'll get a sine of theta term in there.
Okay.
Yeah, absolutely. So in most cases where Hall effect sensors are used, for example, like in disk drives, they are designed so that the magnetic field is perpendicular. You get the maximum effect. Okay, so that's about the Hall effect sensor. What I do want you to understand is kind of like what we did in the homework, because this involves electrostatics as well. You're applying a current through there, and you're measuring the voltage. So you apply a voltage across the length of the material, and you get a current in the y direction, and then you place it in a magnetic field in the z direction. So let's get back to your question. So in this case, the magnetic field is in the z direction, and a voltage of 5 volts is placed across the length of the material, resulting in a current in the y direction. All right, so the current is in the y directions. The electron is moving in the negative y direction because it moves opposite the current. Magnetic field is pointing in the positive z direction, so the electron should be deflected in the positive x direction, and electron is deflected. Oh, this should be an x. Is that what you were talking about?
Yeah.
Okay. Yeah, so that should be in the positive x direction. So that's going to generate a Hall voltage across the xy direction. Okay, and this problem just asks you to calculate what that Hall voltage is using the formula that we just talked about in the slide.
So on that one, is that already showing us the force of the electron? So we do the right-hand rule, we don't have to flip it on that one there? So
Oh, no, you always have to flip it. If you're looking at the movement of electrons, in this case, the electron is moving from
right to left.
from right to left, correct? Right, so electron's moving this way, magnetic field is pointing up. So your thumb is pointing in the negative x direction, but you have to negate that, and so the electron gets deflected in the positive x direction.
I guess some work to do with the right hand.
So it just, yeah, you might want to go through it a few times as we're talking, and we can discuss it. We can discuss it after class if you'd like, or if you want to come to office hours tomorrow. By the way, I'll be available between now and Wednesday. My normal office hours are 3 to 5 Mondays and Wednesdays, but if anyone wants to come by tomorrow, Wednesday morning, anytime, just let me know. I'll make myself available. So. Okay.
So in that picture, is the current going the same direction as the E field?
Yeah, so we put a current in along the y direction, so that's why the electric field is pointing. The electric field that's driving the current is pointed in the y direction. The resulting Hall voltage is going to be in the x direction. Okay, other questions on the homework?
So the whole, it's not gonna be in the exam, right? All of that.
Like I said, if I have something, it'll be on extra credit. It won't be on the main part of the exam.
How about the toroidal coil?
Yeah, I was gonna.
Because that's really confusing.
Toroidal coil.
We just basically say go back to the notes.
Oh yeah.
Derivation.
Yeah, let's talk about the toroidal coil for a minute. This is a good exercise in Ampere's law. All right. So mathematically, this derivation is actually fairly simple. But I want everyone to let's work through the mechanistics of it. Okay. Before we do that, I want to touch on a slightly simpler problem that will get you that'll get you kind of warmed up to this. Has everyone done problem 3? Try to. The main part of problem 3 that I want everyone to understand is that if you have multiple currents, if you just have like a single wire, okay, you can use the Biot-Savart law to calculate what the magnetic field is. You already have the equation for that. That's what we covered here. If you have just a wire, okay, and I ask you, well, what's the magnetic field generated from that wire at some point in space? Here's the equation you can use. H phi is equal to I divided by 2 pi r. The magnetic field drops off as 1 over r as you go away from that wire. What if you have 2 wires? If you have 2 wires, you just add up the contributions of both. Is that straightforward? You find the magnetic field due to this wire, and then you find the magnetic field due to this wire, and you add up both contributions. Yes?
Since the current is going in the opposite direction, do you have to put negative on that and then would cancel out?
Well, let's look at the right-hand rule. Okay, when you're doing the Biot-Savart law, thumb is pointing in the direction of current. Okay, so let's all look at the left side here. Thumb is pointing up, so the magnetic field is going like this.
Yeah, curves around it.
Okay, so at point P, is the magnetic field going into the screen or is it going out of the screen? Into the screen. Right. So it's going in the Z direction. Okay, you see the X there on the Z. All right, or you see the cross there on the Z. I should say X because that will be confusing. The Z is going into the page.
The arrow.
Okay, how about the other one? Right hand rule.
Also,
Thumb is pointing down. So the magnetic field is going like this.
yeah, it's also into the page.
It's also into the page. Right. So those magnetic fields would sum up. So that's why we add them in this problem. All right. Notice that the H1 is the distance is only 0.5 meters from here to P. For the second wire, the distance is 1.5 meters. Okay, so we're just adding up the contributions. Now, getting back to this problem, the toroidal coil. We agree that if we have multiple coils, the currents add up. So we did another example here. We did a circular loop, okay? If you have a single loop, what happens? Like, again, right-hand rule. The current is, my thumb is pointing in the direction of the current. So on the outside, on the front end of that ring, my thumb is pointing from left to right, and the magnetic field is going in this direction, okay? So it points upwards inside the ring, and then it points downwards outside the ring if the current is going in this direction, okay? If you have multiple loops, the contributions are going to add up. So you're just going to increase the amount of magnetic field. So you'll just have a stronger magnetic field inside there. That's what a solenoid is. We were going to talk about this in class today, so we won't have time, but I'll just mention it. A solenoid is nothing but a bunch of loops. So the more loops you have, the more magnetic field you generate in there. But you see the magnetic field is going up in the center of that coil. Getting back to the problem now, this is a toroidal coil, okay? So it's like we took that solenoid, that coiled wire, and we just wrapped it around into a donut. So I want everyone to apply the right-hand rule here, and think about what direction the current is going to flow.
Clockwise.
All right, so on this, the wire is kind of it's wrapped around the donut, right? So on this part here, imagine the right-hand rule. Okay, so the magnetic field is going to go up, and then it's going to go down in here like this. Okay, and the vertical components, interestingly, are going to cancel because on top you have a current going this way. On the bottom, you have a current going in the opposite direction. But what's interesting is on the insides, you're going to end up having a current going in this direction. Sorry. If you imagine on this part of the toroid, where I'm pointing right now, the current is going inside like this, so it's going to generate a counterclockwise magnetic field, or counterclockwise magnetic field. Thumb is going into the screen, and the magnetic field that's generated in this segment is going around like this, clockwise. And the same thing is happening on this side. So when you add up the contributions of all of those coils in the wire, you end up getting a magnetic field that's going through the coil. Okay, and this is the same thing as a regular solenoid. In the regular solenoid that I was just showing you, if you have a current going through a loop like this, you get a magnetic field that basically goes through the loop. All right. Now, if you took that geometry and just bent it around into a circle, so it's like you wrap some coils around a donut, the magnetic field is going to go through the center of those coils, and you'll end up with a magnetic field that basically goes around the circle like this. The magnetic field, you can see here, it's that a green arrow there, H. The magnetic field basically goes around the interior of the donut. Does that make sense?
Is there anything that that's like applied to in any type of engineering or science, like the toroid?
Accelerators.
I believe it's used in accelerators. Yeah, particle accelerators. If you want to use magnetic fields to move subatomic particles, I believe.
And the number of loops.
N is the number of loops, right? So really quickly, because I think this may be all we'll have time for. We have to leave a little bit of time at the end of class today for the evaluations. I want to show you how Ampere's law can be applied here. Okay. Remember, in Ampere's law, the key thing, the strategy in Ampere's law, choose an Amperian contour. All right. How do we choose a contour? First criteria, the current I should go through the surface enclosed by the contour. All right, so in the case of the infinitely long wire, we drew a circle around the wire. Okay, so this is the wire here in the middle. Okay, the wire is coming out of the page. The current is going out of the page. We drew an Amperian contour as a circle around there. And the reason we chose that is because, number one, it encloses the wire, so the current is going through the surface of the contour. The second reason we chose a circle because the magnetic field is going to be the same everywhere on that surface. It's just like when we did Gauss's law with electrostatics, you should choose a contour where the magnetic field is the same everywhere. So you have to look at the symmetry of the problem. So in this case, the symmetry is pretty straightforward because, well, you have, if you have a wire, you know that based on the Biot-Savart law, you know that the magnetic field just goes around the wire like this. So it makes sense to just draw a circle around there. Now, in the case of a toroid, here's what you do. The Amperian contour that you draw is a circle that goes right through the donut here. Okay? That's the strategy. Why do you choose this circle as your Amperian contour? It meets the criteria. Does the current go through the surface of the contour? Yes. And this is what it'll look like. Okay. So the circle, the Amperian contour that we just drew, it looks like this. Notice that the circle is going through the middle of the donut, okay? So the only current that goes through it are the current on the inside, okay? The inside of the donut. The currents on the outside are not counted because it's not in our contour. So this is the contour, C. And then on the inside, you're going to have all of these current vectors, and all of them are actually going into the page. So each one of these current vectors that I'm drawing here represents one loop. All right, now this is the part that you have to think about a little bit, just geometrically. If you follow that current through that wire, what you'll notice is that at the inside of the donut, the current always goes into the screen. Just follow the current in the wire there. You'll notice that on the inside of the donut, the current always goes into the screen.
You mean the magnetic field?
No, current. Current. Notice the direction of the current here. It's going here, and it's going into the screen here, and then it wraps around, and again it goes into the screen here. So when we draw a cross section of that, the reason I'm drawing it like this is because the current is always going into the screen. All right, now when we apply Ampere's law, H dot dl, integral of H dot dl is equal to the current. This is the current going through the surface, and this is the magnetic field, the line integral of the magnetic field. As we have found in our other problems, this just becomes H phi times 2 pi r. Okay, the magnetic field times the circumference of the circle, because that's the length of this contour is the circumference of the circle. So that's where the 2 pi r comes from. H pi is just the magnitude of the magnetic field. The total current here is equal to N times the current running through the wire. Okay, so I should just call this something different so there's no confusion there. This is the total current going through the surface. Total current through surface. Okay, so N is the number of turns in the solenoid, and I is the current going through there. So the magnetic field is then just equal to Ni over 2 pi r. All right, and that's it. That's how you apply Ampere's law to a toroid.
How come we're disregarding the other components of the current, like the current in the other directions?
You mean like the currents outside the contour?
Yeah, or anywhere.
If you include them, your answer becomes 0.
Well, let me just say this first. You don't include them because the contour that you drew doesn't enclose them.
Well, part of that, technically, like we're only counting it when it's going into the page, but it's
Yeah.
a full 360.
But remember, the page, it's an infinitely thin surface.
Okay.
So the part where the wire intersects that plane is going to be directly into the page. Now, to Isaac's point, Isaac brought up this point. If I were to ask you, well, okay, you can use Ampere's law to figure out the magnetic field inside the toroid. What if I asked you to find the magnetic field outside the toroid? Well, in that case, your total current has to include these vectors here, the inner ones, and it also has to include the outer ones. The inner ones plus the outer ones are going to sum up and they're going to cancel each other out. And so the total magnetic field will end up being 0 in that case. Okay, just like we did with some of the other problems where you're looking at the coaxial wire, things like that.
Is that kind of like how when we were looking at the ring, how they're coming out and they're diverging and wrapping around? Are those the diverging ones, kind of? If we look at just when we were looking at the coils and we were seeing how it went through the single ring and then back, how the vectors in the middle came up and the ones that were diverging away at the top, is that kind of what the outside would be, those diverging ones?
Well, there wouldn't be any magnetic field lines outside of it. That's the interesting thing here. The toroid effectively contains the magnetic field inside. So according to Ampere's law, like if you draw a contour or anything outside of it, then the magnetic field is going to end up being 0. So in a way it helps. It's a way to keep the magnetic field lines inside.
I mean, there
So-
would be something there to cancel out the other if it made it 0.
Well, okay. If you have this is an interesting question actually. If you have remember magnetic field lines always have to form loops, right? We decided that because the Maxwell's equation says that it has to form a loop. So, but the interesting thing is in this case the loop is actually inside the toroid. You see the magnetic field actually goes around in a circle. Like that green arrow here, the thing that we solve for, by the way, just to be totally clear, H phi is equal to Ni over 2 pi r. That's the magnetic field direction in the phi hat direction. So the magnetic field actually just circulates around, the magnetic field circulates around here like this. Goes in the counterclockwise direction. So it does form a loop. So we haven't violated any Maxwell equation there.
Yeah, specifically it's actually the magnetic field on that contour. You know, changing the contour changes are in a lot of the other equations. Your
Oh, yeah.
your contour boundary defines
Mhm.
things, but it doesn't define where the field actually is. This only finds the field exactly on that contour.
It only finds it, yeah, exactly in the middle contour there. Like at the center axis of that donut. Okay. So that's how we get this how we apply Ampere's law to a toroidal coil. Let's discard that. I was hoping to go over inductance, but I think just in the interest of time, I will just briefly mention to you that inductance is a way to store energy in magnetic fields, just like capacitance is a way to store energy in electrostatic fields. Inductance is a way to store energy in magnetic fields. And a capacitor, if you think about a traditional capacitor, you think about a parallel plate, right? Metal, dielectric in between. So if you think about a traditional inductor is a solenoid, what we just talked about. And so that magnetic field in the middle stores magnetic energy. And this first slide just shows how the magnetic field inside a solenoid is derived. And the next slide talks about what inductance is and what magnetic flux is. If you are interested in inductance and magnetic energy, you can just take a look at these slides on your own at your leisure. And if you have any questions about it, come and ask me if it involves work or involves anything that you may be interested in. Okay, I do want to spend the last 20 minutes of class on the evaluations. And the evaluations are obviously very important. I want to make sure that you have adequate time to spend on it, and I would request that you do stay here and put some time into it, because the feedback that you give me and you give the department in this class is valuable to us in improving the class and making it better in the future. So tell me what you liked about the class, because those are the things that I would like to continue on and improve upon. And tell me if there's things that you did not like or would like changed, or just constructive feedback. Let me know that as well. I do read every single one of them, so I look at the comments. I don't just look through the tallied scores. So the written comments are the ones I actually do appreciate the most, and that will really help me improve the class in the future. So I would appreciate your time on this. I need a volunteer to take this back, because I will actually be leaving the class and you'll be doing them on your own. And so I just need someone to take them back. Charles, thank you for that. Thank you. So if you don't mind, if you could help pass these out, one per student, and then if you could collect them at the end, and you can drop them off at the ECE front desk.
Okay. I'll help you too.
Thank you.
Professor.
Let's shut this off. Okay, so again, I want to thank everyone for all